This lesson is on related rates, and before we get into what all that means, we want to go over some geometry formulas that you need to remember. These come up pretty frequently when we're doing related rates types of problems, and so just to refresh your memory, a couple of volume ones that are important are a sphere and a cone. Volume of a sphere is 4/3 pi r cubed, and the volume of a cone is 1/3 pi r squared h. That is the height of that cone. Surface area, you'll notice the sphere, if you happen to remember the volume, the surface area is the derivative of the volume. So it's 4 pi r squared. And then a cylinder happens to be two circles, so 2 pi r squared plus 2 pi r h, which was the lateral area. Then area of a circle is pi r squared, area of a rectangle is length times width. Perimeter of a rectangle is 2 length plus 2 width, and then the perimeter of a circle is called circumference. It's 2 pi r. I find that a lot of people mix up the area and the circumference formulas. The circumference is, again, related to the area because it's the derivative of the area, and so maybe that'll help you be able to keep those two straight. But those come up. Others come up too, and as we need them, I'll show them to you. The distance formula, I just say x minus x and y minus y instead of x2 and x1 and y2 and y1, because when you subtract and square, it doesn't matter which one you put first. So there's your distance formula. Now this next one, similar triangles, you may not have seen for a while, and I typed the formula up, but I didn't write these letters in. I was calling this side of the big triangle y, this h, this d, and this x. And I'm calling this similar triangles because this situation happens a lot in the word problems that we do. You may have learned them as two separate triangles, but if you think about drawing these as two separate triangles, the big one has y as this side, but its whole side is d plus x. And then this little one, if you focus in on it, it has the side of h and just x. So it's really two triangles, but they're kind of on top of each other. And so you set up this proportion where you match up the parts, okay? So this long side of the little triangle, which is x, over the h, that's that first one. And then the matching parts, the long side of the bigger triangle, which is x plus d, over the y. That's how I got that fraction, and just setting up that proportion. Again, this comes up sometimes, so hopefully it'll make sense having refreshed your memory right here. Okay, the steps that I'm getting ready to tell you for doing related rates problems aren't going to make a whole lot of sense until we actually get into a problem, so just bear with me. The first and most important thing to do is to read the problem completely and reread it until you understand what's going on, because you're not going to get too many places if you don't get what's happening. And I always sketch a picture and label that so that I know what's working where. The third thing that we want to do, and it's really important and I always do it, is to write down our given information and stuff you just know. Sometimes you just know things, and you'll see that as we come up on problems. And the fourth is to write an equation that relates the variables. Occasionally they'll give it to you, but most of the time they don't. And this is why I went over all those geometry formulas. Most of the time you're going to have to figure out which one to use. They do throw trig in and things like that. And the last example I have on this for us to do does have trig in it. Now, I want you to circle, highlight, star, something, this right here. A lot of times with a cone, and we'll do this in optimization as well, we're going to use the radius and height information to get down to one variable. That's going to happen quite often, and it's typically with the cone and not the other things. But again, we'll use that also when we do, or that concept when we do some optimization. When we do the differentiation, the implicit differentiation here, we're going to do all variables like we treat y. So the derivative of x will be x prime, the derivative of p would be p prime, and so on. All variables are treated like we treat y when we do implicit differentiation. And the last thing that we do is we substitute into our equation our given or known information and solve. Okay, our first example is the classic related rates example. It's a ladder leaning against the wall, and so I'm going to sketch, here's my wall and my floor, and here's a ladder leaning against the wall. The bottom of the ladder is sliding away from the wall, and they want to know how fast it's sliding down the wall when it's 12 feet above the ground. So imagine for a second if you were pulling the bottom of this ladder out, and you pulled it at a steady speed. The top of the ladder starts slowly, but then as gravity hits it more and more, it drops faster. So the rate that this is dropping is related to the rate which we are pulling away here. And so that's why this is called related rates. Okay. I tend to, in the ladder problem or in problems that make triangles, label the horizontal x, the height or the vertical y, and then the ladder either d or z. I'm going to go with z this time. And I just, you got to make variables to get somewhere. So I'm going to make a list of what we know. So x, y, and z. We're going to look at it at the split second that that ladder is 12 feet above the ground. So at that split second when the ladder is 12 feet above the ground, that y is 12. The other thing that we know is that first sentence, the ladder is 20 feet long. So that z is 20 feet. And we're assuming it's a regular ladder, not an expanding ladder. And so we know those two things. X is something that I would put in the category of you just know or you can figure out. So because these are related by a triangle, I can do the Pythagorean theorem and figure out what x is. So x squared plus 12 squared equals 20 squared. And that will make x squared 256. So x is 16. So I can write that 16 up there and I know all that. The thing that we haven't addressed in this problem is the rates of these things. It says the bottom of the ladder is sliding away at 2 feet per second. That is the rate of change in x. I like to use dx dt because it helps me with my units, but you can use x prime. That would not be wrong. But that is the derivative of x. And so that is 2 feet per second. And then how fast is the ladder sliding down the wall? That is how fast the height is changing. So I'm trying to find dy dt or y prime. So I like to put a question mark for what I'm trying to find. And obviously if I have a rate for x and a rate for y, z has a rate as well. And this is another thing you just know. Because this is not an expanding ladder, the length of that ladder is not changing like the length on the floor or the wall is. So that ladder is not changing, so its rate is 0 feet per second. Now, that's all of my given information. The next step is to come up with an equation that relates these things. And obviously, I've already used it one time to get a missing side. The three sides of this relate using Pythagorean theorem. So I'm going to say x squared plus y squared equals z squared. That's the equation that relates the things. You do not plug in right now. If you plugged in, you would just be backing this over here. It doesn't help. It doesn't factor in the rates. The way we get to the rates is by doing that implicit differentiation. But again, you treat every single variable like you treated y before. So I'm going to do a chain rule here. So 2x, and then the derivative of the inside, you can put x prime or dx dt. Just pick a notation and stick with it. and then plus, again, it's a chain rule, so 2y, derivative of the inside would be dy dt, and then the z would be 2z dz dt. Now, what's going to happen every time you have a Pythagorean theorem problem is you're going to get these 2's, and I can go ahead and divide the entire thing by 2 and get rid of those because everything has a 2, and it's just going to make my numbers a little bit easier to work with. You don't have to do it, but if I'm doing Pythagorean theorem, I've done this enough to know it just helps. After you've taken your derivative is when you plug in. So plug in for x dx dt, y dy dt, and z dz dt. Okay, so we plug in. X is 16, dx dt is 2, y is 12, we don't know dy dt, that's what we're trying to find. Z is 20, and dz dt is 0. And so when we go to solve this, we have 32, 12 dy dt, and on this side you just get 0. So I'm going to subtract the 32 and get negative 32 on that side, and then divide by 12. So negative 32 over 12, and that does reduce to negative 8/3. Now, this is why I like to use this notation, because I can think about the units. What are the units of y and what are the units of t? So y is a distance from the ground to the top of the ladder, and so that distance in this problem is measured in feet. And then our t, our time, is measured in seconds because I can tell from my given they gave me things in seconds. Now, the units are incredibly important because sometimes on the AP exam you get a point just for having correct units, so you want to not miss out on that. Again, if you use y prime over here, that's fine. You just have to remember what that stands for. And so here I'm looking for negative 8/3 feet per second. Why would it be negative? Because the ladder is going down the wall. So that makes sense. That distance is shrinking. So that distance is getting smaller. So negative derivative there. Okay, example 2. We have a snowball that's melting so that the radius is decreasing at a uniform rate of 1 centimeter per second. How fast is the volume decreasing when the radius is 4 centimeters? This is one you wouldn't necessarily have to draw a picture on, but if you wanted to, here is our snowball. And here is the radius of that snowball. So what do we know? We know that the radius is 4 centimeters, and it's decreasing at a uniform rate. So that would be dr dt, the change in the radius. And because it's decreasing, I'm going to say negative 1 centimeters per second. Now, we can also, in this case, get the volume of the snowball. You'll notice that we don't end up using it, but the volume would be 4/3 pi times r cubed, which would be 256 pi over 3. We actually don't end up using that, and you'll see why in just a minute. Alright, the thing that we're trying to find is how fast the volume is decreasing. That's a rate of change of volume. So dv dt, I'm going to put a question mark. Okay, so now that we have everything, we need the relationship between the volume and the radius, which is that same formula we used a minute ago. Volume of a sphere, which is 4/3 pi r cubed. And again, you don't plug in right now, you plug in after you take the derivative. So the derivative of volume is just dv dt. Because we don't have a chain rule or a product rule or anything right there to make that more complicated. It's just one variable. And then on this side we have to remember that 4/3 pi is a number, so this is just a power rule. So if I multiply by 3, I get 4 pi r squared, doing that outside, and then the derivative of the inside, chain ruling it, is dr dt, or if you're using the primes, r prime. This is the point where you plug in, and this is why I say we really didn't need that volume, because we ended up just having the derivative of it in our formula. So that is what we're trying to find, so that's still going to stay dv dt. and I'm going to plug in the r of 4, and make sure you square that, and then the dr dt of -1. When you do that, 4 pi times 4 squared times -1, you get -64 pi. And if you think about the units, volume in this case would be in centimeters cubed. And time in this case is in seconds, so this is centimeters cubed per second. Okay, 3 is where we get to that cone situation that I was mentioning before. We have a water tank that's in the shape of an inverted cone. So what we mean by that is the point is down. Okay. And it has a height of 12 feet and a radius of 6 feet. And water is being pumped in at a rate of 10 gallons per minute. How fast is the water level rising when the water is 3 feet deep? Okay, so the first thing that you want to do before anything else here is come up with that relationship between radius and height. The 6 and the 12 are for the entire cone. If you think about it, the water is coming in. The water is not full yet. It's somewhere down here. It has some kind of radius and some kind of height that we don't know at the moment. But these are similar figures, so the relationship is going to be the same. So here the radius is 6, the height is 12. So 2 times the radius equals the height. So no matter at what point the water is, 2 times this radius will always equal this height of that water. I could also write that as half of the height equals the radius. And so I usually write both and then decide which one I need later. Okay, then I'm going to write down all my given. The first thing is that 10 gallons per minute. That is gallons per minute. That is volume. So change in volume over time, dV dt, would be 10 gallons per minute. The next, how fast, so the rate, is the water level rising. The water level rising, they're talking about that height. So we're trying to find dH dt. And then when the water is 3 feet deep. So we know the height of the water is 3 feet. The other thing they give us is that 1 gallon is 0.1337 feet cubed. And the reason they do that is because this was given in gallons, this was given in feet. I need the units to be the same. So if I multiply 10 times that number, I get 1.337 feet cubed per minute. I can convert that. I'm just converting from gallons to feet cubed so that I can work with them in that same equation. Here's how you decide what variable you want. Because I'm trying to find dH dt and they gave me h, I need the variable in my formula to be h. What formula is that? That is the volume formula for a cone. So volume is 1/3 pi r squared h. If I don't replace that r, I get a product rule because r is a variable and h is a variable, and I have no information about r or the rate of r. I could find what r is, but I could not find the rate of r, and I would be stuck. So because I have information about h and I'm trying to find h, I'm going to replace the r with 1/2 h, the relationship that I found. So 1/3 pi 1/2 h squared replaces the r. Then I'm going to square that 1/2, square the h, and simplify this formula. When I square the 1/2, I get 1/4, which I can multiply by the 1/3 and the pi and get pi over 12. I also have to square the h and multiply by h, so I get h cubed. This is my new formula. It's a lot easier to work with, and it's just a power rule. Now I'm ready to take the derivative. So the derivative of volume would be dV dt, or V prime. Here I'm going to do a chain rule, so 3 times pi over 12 would be pi over 4 h squared, and then the derivative of the inside would be dH dt. Now I can plug in. dV/dt is 1.337. The h is 3. And the dH/dt is what I'm trying to find. So I get 1.337 equals 9 pi over 4 dH/dt. And then I'm going to divide by 9 pi over 4 or flip it and multiply and get 0.189. And again, I want to think about units. And because I'm in this notation, I just think height units over time units. The height in this is measured in feet. The time is measured in minutes. So feet per minute. So example 4 is another cone problem. And this is a good one to pause and see if you can get anywhere on it. Try writing down your given. Try coming up with your formula. Try replacing your variable and see how far you get. So pause. So now you can check your work. With the cone, they told us it had a height of 10 and a radius of 2. And so that relationship would mean that the height was 5 times the radius, or the radius was 1/5 of the height. So I don't know which one of those I'm going to use till I get over here. My given information is that liquid's being poured in at 1 centimeter cubed per second, which is a change in volume over time. So that's dV/dt. How fast the radius increases is dr/dt, and that's what we're trying to find. And if we know that the height is 4, the radius would be 4/5 just by knowing that relationship. Then we come to the volume formula, and you decide, do you want r's or h's? And since they ask about radius, you need the variable to be r. So you need to replace the h with the 5r that we found over here and simplify. So I just have to multiply that 5 in front and multiply the r with the r squared. So this is the new volume formula. And then I take the derivative. The derivative of volume is dV/dt. Here I have a chain rule, so I do 3 times the 5 pi over 3, and the 3's cancel, and I just get 5 pi, and then I subtract 1 from the power and get 2. And then times it by the derivative of the inside, which is dr/dt. Then I plug in. I know dV/dt is 1, and r is 4/5. I have to square the 4 and the 5, and then the 25 and the 5 will reduce, and the 4 squared is 16. So that's where I got the 16 over 5 pi dr/dt. And then I need to divide by 16 pi over 5 or flip and multiply. So I get 5 over 16 pi centimeters per minute. Now how did I know it was centimeters per minute? Again, r is measured in centimeters, t is measured in minutes. So that's my units here. And you could get a decimal here, and that will be fine. Just make sure if you're dividing by the 16 pi in your calculator that you have all of it on the bottom, or put it in parentheses so you make sure it's all on the bottom. And you round to 3 correct decimal places.